Greetings and welcome to another installment of QuantSlab. This is 19 in our basic application series. This time around, yet more on proportions. It's yet more because we have already learned quite a bit about proportions, not only earlier here in this basic application series, but going way back to our QuantSlab foundational series. Such fond memories. Seems like just yesterday. Yesterday. Greetings and welcome all of you crazy QuantSlab crew cats. This is negative 2,742 of our foundational series, and this time around we're going to kick off our introduction where we introduce our introducing of our intro to our introduction of our introducing of our intro. Well, I think that was one of those ideas that looked better on the storyboard than as it actually came out, and besides, it wasn't really all that long ago. Anyway, back then we learned, among other things, from a data science perspective, we may think of proportions as a rising force in at least three different settings. We can talk about a proportion as a population parameter. We can also talk about a proportion as a sample statistic, and also as a random variable implicated by theoretical random sampling. Now, this last setting is quite a bit more challenging to grasp than the other two, but with familiarity comes understanding. From a notational standpoint, we commonly use lowercase upright p to denote a proportion in a population, that is a parameter. To denote a sample proportion, that is a sample statistic, we keep the same p here, but we put a little hat on it, so that's nice, got a little hat there. As a random variable, we keep the hat, and we use an uppercase leaning or italics p here on QuantSlab. In our terminology and symbols microseries, we saw that we can put a little subscript here on our proportion symbol to remind us and make clear to anyone else exactly what it is we're talking about. Okay, so let's roll things back here a little bit. What is a proportion? Where does it come from? We can think of a proportion as a quantity describing in the aggregate the prevalence of some category or property among a collection of elements or observational units. So, for example, we can consider the proportion of occupied seats in a small conference room. So to each of our units, the chairs here, seats, we can ascribe an attribute, occupied status. And in this way, we can calculate our proportion of occupied chairs here. For another example, we may have a waddle of penguins here returning from a nice, refreshing swim and wonder what proportion are named Banu. Seems like a reasonable avenue of investigation. Assuming we have access to these penguins' first names, we can calculate our proportion. We have 16 penguins here, and look at that. Two of them are named Banu. It seems like it would be a little bit confusing for them, but then again, who are we to stand in judgment of a bunch of penguins? Another thing we talked about is creating an indicator attribute. An attribute where we have converted a categorical label into a 1 or a 0. Admittedly, this extra step may add a little additional complexity, but it is very useful. By indicating over a categorical label, we are creating a quantitative attribute. And one consequence of this is that it turns out that the proportion of the category is the same as the average of the indicator, our indicator. Another important consequence, and one we have not introduced here on QuantSlab, is that now that we have our indicator attribute, we can quantify how varied this attribute is. The so-called variance is a very useful way to talk about how varied a quantity is. And we have not yet discussed how to calculate variance. But it turns out that for a proportion, we can calculate the variance of our indicator attribute simply as a function of the proportion value itself. And this, by the way, is quite different and much more simple, fortunately, than with quantitative attributes more broadly. It turns out that the variance of our indicator is simply the proportion value times the value subtracted from 1. So, for example, if our proportion is, say, 5/7, then the variance of our indicator attribute is simply 5/7 times 2/7, which equals 10/49. For another example, if our population proportion is, say, 1/8 here, then our variance of this attribute indicator would simply be 1/8 times 7/8, which is 7/64. Proportions, moving on, whether they be population proportion, sample statistic, or even random variable, are very easy to plot and easy to convey by table. And lastly, here for this edition, we may speak of a proportion within an infinite population. And if you're not familiar with this, this may seem bizarre, since this might suggest that calculating our proportion would require dividing by infinity. But this is not an issue, it turns out. For one thing, we can simply define a proportion value within an infinite population. And we've already done this plenty of times here already on QuantSlob. Or we can conjecture or hypothesize a proportion value within an infinite population. No problem. Moreover, using commonly established properties of numbers, we're allowed to assert things like the proportion of even integers within the collection of all integers is 1/2, or that the proportion of real numbers in the unit interval that are less than 1/5 is 1/5. Not at all an issue. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more QuantSlob.